This is my mechanical engineering lab 3 report. The outline for the report. Our objective was to conduct free vibration experiments with a cantilevered beam and different displacement parameters. We also wanted to compare experimental values to theoretical ones to determine the efficacy of our experiment and reinforce our beliefs shown by theoretical data. The experimental setup was as shown. First, we created a Wheatstone bridge to measure values from the strain gauge. The strain gauge was connected to an aluminum ruler, which would give us an idea of how it was straining as we displaced the tip of the ruler. This ruler that was then secured to the edge of the table with a clamp. A finger was used to displace the tip of the beam for cases 1 through 2. For cases 1, excuse me. For case 2, a coin was dropped on the tip of the ruler to create an impulse excitation. For case 3 and 4, two different types of tape were secured under the ruler to create a damping effect. First, we wanted to get strain gauge sensitivity and equivalent stiffness calculations. This is to observe effects on a static load on a cantilevered beam. The initial voltage data was first collected and plotted against its displacement as different loads were applied to the edge of the ruler. The equivalent stiffness was calculated using the curve of the best fit line and was calculated to be about 30.2 with a strain gauge sensitivity of 2.8. In the first case, the edge of the beam was depressed by a finger by about 50 millimeters or so, and then released. The graph here shows the fluctuation in voltage readings as the beam or the ruler oscillated. The strain gauge sensitivity was estimated with prior voltage and displacement data, and the trend of data is predicted. The graph reflected the real-time observations of the excitation and displacement of the beam before it was released. This entire oscillation was about 7.5 seconds, and the graph of the data that was collected was expected. The initial voltage, which was seen in the graph before, was converted into displacement measurements and matched what was observed in real time during that experimentation. Hmm. Using the data we collected, we were able to calculate the natural frequency, damping ratio, and damped natural frequencies on Mech Lab. The damping ratio was discovered using the curve fitting method. Here, a curve fit was attached or applied over the displacement graph, and then we use a series of calculations to determine a damping ratio of about 0.00047. This would be the case for both case 1 and 2 since they were displaced and excited in the same manner, roughly, since you do have to factor human error and experimentation. The first natural frequency and the damped frequency were determined through calculation, where the damped frequency equals the square root of 1 minus the natural frequency squared. Since this is a very lightly damped system, already suggested by the low damping ratio of the first case, we assumed that the natural frequency would be the same as the damped frequency. This can only be assumed under a heavily underdamped system, however. Next, we wanted to compare the theoretical versus our experimental values. The equation for the theoretical free response is as shown, and we inputted the data we collected to create a theoretical graph that we could place against our experimental one. Although the theoretical data is skewed to the left, it doesn't consider the first second or so of initial displacement. However, its trend is similar to our experimental data. This could be because of experimental calculation error should take into account that minute, that second of initial displacement. However, the trend is very optimistic, seeing how it copies the gradual decrease in oscillations as time progresses. Next, we wanted to determine the spectrum of the first case. The spectrum was computed using FFT to split the signal into its individual frequencies. The large peak near 0 Hz indicates an error, which is probably from the an error in the removal of the mean. The second peak, however, at around 47 Hz is more likely to be the natural frequency of the beam. This large disparity between the estimated frequency and the experimental frequency is most likely because of an calculation error in the estimates. If you go in the earlier slides, you'll see the estimated frequency was about 7, and this is clearly not the case. The impulse excitation was implemented by dropping a coin onto the beam, ensuring it would bounce off. The same configuration in case 1 was used. Although there was difficulty getting the coin to graze the beam in the right way, the displacement aligns with physical observations. Like previous spectrum diagram, this one was computed using FFT. Unlike case 1, the spectrum is a lot more clear. The noise floor is consistent, and we see, as expected, that the natural frequency is also at around 47 decibels. The disparity between this experimental and theoretical data is the same. However, because they both share what we assume is a natural frequency of 47, we can assume that the error lies solely in the calculation of the estimate. Next, we did viscoelastic damping. As shown in the picture below, that is the setup for the lab, and in this instance, strips of tapes were placed under the ruler. The beam was depressed and then allowed to oscillate. We used two different types of tape to demonstrate two different types of damping, Scotch and carpet tape. Scotch provided light damping, while carpet tape provided heavier damping. As the issue increased with the layers of tape, the carpet damping settled the fastest out of the three, where the undamped case settled the lowest. Although the differences in the damping ratios are small, you have 0.0047, 0.0063, 0.0089. The effects are very clear. In summary, we saw a lot of things we expected. The same or similar natural frequencies for case 1 due to the same kind of load being applied, the higher damping ratios as damping increased, and Fn and Fd being equal because of a lot of underdamped case. However, what we didn't expect was the low estimated natural frequencies in comparison to the experimental values. These inaccurate values were likely caused by calculation error done in Mech Lab, and that is why we can see a very big disparity. In conclusion, we learned that not only can a strain gauge be used to measure dynamic tip displacement, it can also be used to determine the frequencies of the beam. The type of materials used in on these beams also carry a very big relevance in what the damping ratio of these systems are going to be. When determining the fundamental natural frequencies, elimination of the mean is also very important. Last but not least, although although there were several disparities between our experimental and theoretical values, we can mostly designate these as calculation errors, and the graphs reflected what we expected to see of the system despite these these numerical errors. Thank you.